Sometimes we have to work with independent random variables x1, x2, xn, and we want to consider some linear combination, summation ai xi, where these ai's are all real numbers. So it will be a good idea to have some technique which, when you give me distributions of x1, x2 and xn, they are independent, you can quickly find out their distribution. Now, one such technique is provided by what is called the characteristic function, abbreviated to CF. The definition goes like this. Suppose you have a random variable x, then its characteristic function is going to be a function which I shall denote by the Greek letter xi. This is not epsilon, xi, which will be defined from R and take value in complex numbers. And it is defined as expectation of e to the power itx. This t is the dummy variable in R. Now this is quite confusing at first, because first of all, what is meant by this complex quantity? Where did it come from? And what is meant by expectation of this complex random variable? So far we have been working with only real things. Now it is not a place to explain the underlying motivation. It actually came from physics. Came from something called the Fourier transform, and this is just an application of Fourier transform. But let me explain the technicalities. What is meant by a complex random variable, how you take expectation, and how you do math with them. When someone says that z is a complex random variable, they mean that z can be written as x plus iy, I is the complex I, for real random variables, that is the random variables we have been working with so far, xy, just like complex numbers, the real part and the imaginary part. Now when I say I want to take expectation of z, what do I mean? I mean expectation of x plus I times expectation of y. So I, being a constant, is naturally outside the expectation. Remember, this is not a theorem, this is very natural, but this is what we take as the definition. Now if any one of them fails to exist, at least one of them fails to exist, I will say that this does not exist. If there is any infinity or minus infinity in them, I will say expected value of z is infinite. Remember that in case of complex numbers, we have just concept of infinity. There is no concept of minus infinity and plus infinity separately. So even if one of them is infinite, immediately this is infinite. If one of them does not exist, immediately this does not exist. Both of them finite, then this is also finite. In our case, we was working with this complex random variable e to the power itx. Remember, t is real, x is real. It is I which introduces the complexity. Now we know from Euler's identity that the real and imaginary parts of this complex exponential are like this. So when I take expectation of this, I have in mind expectation of this plus expectation of this. Both these quantities are bounded quantities between -1 to 1, so their expectation must exist and be finite, actually between -1 to 1. So this always exists for every real value of t. Now when you want to compute this for any given x, it is not usually convenient to find this expectation and this expectation separately. It is better to do calculus directly with this complex thing. So let's learn a little bit about complex integration and differentiation. Suppose we have a function from R to C, then again, as usual, we will split it up into real and imaginary part. And when you are given this function, we can differentiate this in the most obvious way. You differentiate the real part, you differentiate the imaginary part, do this, and you will get derivative of f. And if even one of them fails to exist, then you say it is not differentiable, usual. Now, when you want to integrate, same story, you can integrate them separately and then add. Integral of fx dx is integral of gx dx plus integral I times integral of hx dx. So you see, though we are working with complex valued functions, when you differentiate or integrate, we are only working with our traditional real valued functions. Now, we will learn more about such things later in your complex analysis course, and things will become more generalized there, because this R will also be replaced by C, and then life will be quite different. But as long as you have the domain R, the very straightforward generalizations all work. Let's just work out the characteristic function of one random variable. Suppose x has density with, this is the density. Your job is to find the characteristic function of x. So we just employ the definition. It is expected value of itx. Now I can split it up into sine and cos, but I will not do it. I will directly use the formula. So it is from 0 to infinity. Then the thing that I am trying to find the expectation of times the density 3 to the power minus 3x dx. And then I will just combine the entire exponential as e to the power it minus 3, the entire thing times x. Now I shall use just complex integration as if it is real integration, which is justified by what I said earlier. So you can treat this as a constant. Who cares that it is a complex constant? Treat it as just a constant and it will give you the correct result. So it will be 3 divided by it minus 3, and then you will have e to the power it minus 3 and of course x 0 to infinity. Now as you let x go towards infinity, thanks to the presence of minus 3, this thing will go to 0, and when you put 0, it will be just 1. So it will be minus 1. So it is 3 divided by, I have made it 3 minus it, from it minus 3. So this is the characteristic function of this distribution. Find the characteristic function of x if x has uniform distribution over minus 1 to 1.